Okay, so chapter 12, and here's how we represent these curves. We represent these curves like this. We use what we call, well, the title of the chapter is vector-valued functions. Vector-valued functions. And our notation is this. We have a vector-valued function, r of t. It's a vector. Its x component will be an x function of t. Its y component will be a function of t, and its z component will be a function of t. You know, I guess what's definitely brand new here is we're going to have vectors. We're going to have vector-valued functions. I guess chapter 11 was vectors with numbers, right? Vectors with numbers. Now I got vectors with variables. Okay, it's going to be a vector-valued function, and the variable is t. And you'll plug in a certain t, and you'll get an x and y and z component for your vector. By the way, again, if it's 3D, we refer to this as a space curve. But we can definitely deal with plenty that are 2D. Here, I'll just write this, but x of t, comma, y of t. Just a two-dimensional curve in the xy plane. And we call that a plane curve. They use the word plane curve, P-L-A-N-E. And, you know, rather than give you a bunch of theory, you know me, I like to do an example. So I'm going to get to an example right off the bat. And my example is this. Here, it's very basic at first. I like beginning basic examples. Here is a two-dimensional curve. It's a vector-valued function. It's a very easy one. T squared. It's two-dimensional. You can tell it's two-dimensional. And and really, okay, you guys, I want to plot points. I want to make a little chart and plot points. Now, you know, this is rather tedious, but it's pretty easy here at first. I'm going to plug in various values for t, -2, -1, 0, 1, and 2. That's good values for t, and I'm going to plug them in and see what I get. When I plug in a -2 for t, of course, I get a vector. The answer is a vector. That's why, see, this is an interesting function. The input is a real number. The output is a vector. It's a vector-valued function. The input is a scalar, t. The output is a vector. -2, 4 is the first. Plug in a -1. It's fairly easy. -1, 1 is your vector. Plug in 0. You get the good old vector 0, 0. Which plug in a 1. You get the vector 1, 1. And plug in a 2, and you get the vector 2, 4. That's enough for me right now. These are position vectors is what these are. These are position vectors. What you do is you plot these in the xy plane, or if it was a space curve, we'd plot it in space. But we plot these in the xy plane. Look at what they look like. Here we go. I'm going to plot the vector -2, 4. And of course, when you draw a vector, you start at the origin, and it takes me over 2 and up 4. And there's a vector that just took me from the origin out to here, and that's the vector -2, 4. It took me to that position. You know, we know this now, but you know, I don't like to say that this is a point. It's not a point. It's a vector, but it is the point. I'm sorry. The vector -2, 4 takes me out to the point -2, 4. So there is a connection, definite connection there. Here, I'm going to plot the next one, -1, 1. -1, 1 is this vector. Take me to that point. 0, 0 ain't much of a vector. It goes nowhere. It's kind of right there. 1, 1 is a vector that goes over 1 and up 1. And 2, 4 is a vector that goes over 2 and up 4. and I can plot more, but I'm happy with this, I think. The curve is the connection of all those endpoints. I mean, so these position vectors are taking me out to these positions. These position vectors are taking me out to these points. You know, what I'm really interested in is these points. I'm interested in these points where this ends up, and then I sort of connect those dots, and by golly, look what I have. What do you call it? A parabola. I mean, it's a good old, maybe this kind of slipped past you here. Maybe you saw it coming, maybe you didn't see it coming, but this relationship between x and y here is fairly basic. If x is t, you know, by the way, I'm not really finished with this discussion, but I'm teaching you how to plot a vector-valued function. And I'm just plotting points, but you're plotting vectors that lead to these points. And then you connect those points and you have this curve. You know, chapter 10 was all about parametric equations. Parametric equations look like this. So here's a little chapter 10, parametric equations.
11.
No, 10. At the end of Cal 2, in chapter 10, you could have had a nice discussion on parametric equations. We just discussed some parametric equations in 11, though we did discuss parametric equations of a line in space. We did. But back in 10, there was a more general discussion of parametric equations of all kinds of shapes. You weren't in 3D, though, in chapter 10. You were in 2D. But just... this is the same thing as this. And again, I don't, maybe if you're not too familiar with chapter 10, what I want to say is it's the same thing. But there is one subtle difference. When you plot these t-values, these really are points. There's no vector involved here. There's no vector involved here. By the way, what you might see here very clearly, though, is that if x is t and y is t squared, if you substitute this x down here for this t, what is the relationship between y and x?
Y equals x squared.
Y equals x squared. By the way, this is the way we talked before chapter 10 and before chapter 12. And I mean, this is good old, what we call a good old rectangular equation in rectangular coordinates. That's, you might never have had a name for that back in the day, but good old XY relationships are called rectangular equations, rectangular coordinates, rectangular equation in rectangular coordinates. The XY coordinate system is the rectangular coordinate system. Our XYs and Zs are the rectangular coordinate system. This is called parametric equations from chapter 10. And now I've got this kind of almost a third way of discussing this, and it's with chapter 12, vector-valued functions. And it's better. It really is better. It really is the language of the future. And I think by the end of the day, you'll see why it's better. What's funny, though, it is a little cumbersome. With all these position vectors I have to draw, it takes me out to this curve. You know, the truth is I'm really interested in the curve, not the position vectors. And all those position vectors sort of clutter up my curve. I mean, really, I'd rather not see those. I'd kind of like to erase those after I find where they go. I'd like to erase those and look at the curve. Hey, you know, with good old rectangular coordinates, you know, when you draw a parabola, how do you draw a parabola? You go like this. Look, you draw a parabola and you put arrows on it, right? Because it's going up. You know, it just goes up forever, you know, so you put those arrows on it. Listen, you may have learned this in chapter 10 with parametric equations, but here it is again in vector-valued functions. We want to show orientation on the curve. We want to show the direction. Showing orientation means show the direction of increasing t. By the way, you know, this is an x-y position axis plane here. You know, there is no t anywhere unless you subtly, you know, make little notes like this. When we were here, what was t? -2. When you were here, t was -1. When you were here, t was 0. I mean, if you add these little notes, now t is on your graph. But now you can tell the direction of increasing t. This is moving in this direction, so to speak. So we put arrows like this. Yeah, and that was a topic, again, back in chapter 10. I think you guys have already admitted to me maybe we didn't do a great job in chapter 10. But that's okay. I think we can recover. We can recover here in chapter 12. But anyway, you don't put the 2 arrows on the end, like that would be misleading, actually. So it's tempting to draw a parabola and draw this, but that would mislead me here in chapter 12. Vector valued functions. I need to see the direction of increasing t. And it is, listen, this is just math. And my x and y and t can be anything. I mean, it can be anything. But it is kind of fun to think of it like physics and to think of it as this. Think of t as time. No, just I mean, this is math, so we don't put physical relationships on this math. But it is convenient to think of t as time, and you're a little particle, and you're traveling on this path. So this is the path you're traveling on, and this is the places you're at. This is the location you're at these times. It's cool to think of it like that. I mean, but then you're making it a physics problem in a way, but that's cool. It's a good way to think. It helps you think. You're a little particle is traveling on this path, and this is where it's at. This is its position, this is its position at these times, if you want to think of t as time. Yeah. Let's look at another one. I think I said enough. Let's look at another one. R of t is 4 cosine 3t, comma 4 sine 3t. This is what we would call a plane curve, a vector valued function in 2D, a vector valued function in 2D. This is where some recollections from chapter 10 might help. If this were written as parametric equations, I wonder if you would know what this is. I mean, your x is 4 cos 3t, your y is 4 sine 3t. I can plot more points. I'd kind of like you to just tell me what it is. Do you know what it is? I mean, I want to know what its graph is. You know, x is cosine and y is sine. That should make you think of maybe, who else acts like that in your old history? Back in 3rd grade when you studied the unit circle, x was cosine and y was sine. Anyway, this is a circle. Oh, sure. This is a circle of radius 4. Now, I guess to really prove it, I would plot 1,000,000 points. I should make a chart and plot 1,000,000 points. Here's another way to prove it, though. Watch. This is from chapter 10. I'm sorry, but I'll do this. If this was written as x equals 4 cos 3t, that's what it is, and y is 4 sine 3t. I mean, you saw what I did last time. How I had x equals t, y equals t squared, and I discovered the relationship between y and x, which was y equals x squared, so it's a parabola. Well, watch how I do it this time. I'm going to divide by 4, and x over 4 is cos 3t. Y over 4 is sine 3t. And can you tell me any true facts about cosine and sine? I know a true fact. I know that cosine squared plus sine squared is 1. If I use that true fact right now, I will see this x and y relationship. This work I'm doing is called trying to eliminate the parameter so you can see the relationship between x and y. We're trying to eliminate the parameter to prove to you the relationship between x and y. So I'm going to say right now, what did I say a second ago? Cos squared plus sine squared equals 1. Well, that means that this squared plus this squared equals 1. And if I write that down, this squared plus this squared equals 1. That's an x squared plus y squared. They're both over 16. If you don't mind, I'm going to move the 16 to the other side, so I'm skipping a couple algebra steps. But this is this. Are you with me? That was a long little... What?
That was brilliant.
Thank you. That was a long little sort of a proof that proved to you that he's a circle of radius 4, centered at the origin. This is his rectangular equation. This is his parametric equation from chapter 10. This put into a vector format is what we're studying in chapter 12, vector valued functions. He's a circle of radius 4. Yeah. And I'd like to know his orientation. I want to know, is he going around clockwise or counterclockwise? Do you have a guess? You can guess. You get 50-50 shot at it. I mean, it's important to me to know his orientation. Is he... it is... Well, I guess the one way to tell would be to plot a couple points. Here, I'll get rid of this. I'm going to plot a couple points. Watch this. If t is 0, you plug it in and you get a vector. What is the vector? The cosine of 0 is 1. You're right, 4, 0. Now that's a vector. It starts at the origin, and where does it go? It goes out to the point 4, 0. The vector 4, 0. I mean, here it is. It's a position vector. It takes me to this position. And I'm there when t equals 0. Here, let's plot, watch this. I'm plotting pi over 6. I'm going to plug it in. I'm going to get 3 pi over 6, which is pi over 2. And the cosine of pi over 2 is? 0. Calculator could help, but sometimes you remember this stuff from 3rd grade. I'm plugging in pi over 6. It's 3 pi over 6. That's pi over 2. The sine of pi over 2 is a 1 times 4. That's 4. So what's this position? Right here. So I'm right here at that 0, 4. And I'm there when t equals pi over 6. So I'm pretty confident I'm moving this way. I already knew that, but I just got that memorized. I got it memorized that when x is cosine and y is sine, it's moving counterclockwise. It starts there and it moves that way. I've kind of chosen to memorize that. When x is cosine and y is sine, it starts here and it moves this way. Hey, how long do you think it takes to get all the way back to where it started?
2 pi. It has to equal 2 pi.
T equals.
It has to equal, it has to 3 times 2, whatever that has, the outcome has to equal 2 pi. So it cosine 2 pi.
Okay, you're on to something. Now hang on, watch this. How long did it take me to do a quarter of it? Pi over 6? Well, guess what? Another pi over 6, another pi over 6, another... Let's see, wait a minute, that's 1, 2, 3, 4 pi over 6, or 2 pi over 3. So it gets back here in 2 pi over 3. And you know what you call that? The period. The time it takes to complete one cycle. The time it takes to complete one cycle is the period. Hey, if you remember your trig, how would you calculate the period of this trig function? It's totally affected by the 3, and it's sort of what you were saying, Matt. But the kind of the rule is the normal period of cosine is 2 pi. When it's got a coefficient on that t, the period is 2 pi divided by that number. Oh, yeah, 2 pi over 3, like we just sort of figured out.
That makes sense.
Okay. Are you ready? I'm gonna do something else. I think I'll get rid of this guy. What am I doing? I'm sketching a plane curve in 2D using this new thing called vector valued functions. These position vectors take me out to the point, and then I draw the curve, and then I kind of don't want to see these position vectors. They kind of clutter up my picture, but there's, you know, if I plotted points, I could have all these position vectors. They'd be, here they are, they're all taking me out to this position. You know, there's millions of them, but they kind of, the actual curve is the, connecting the endpoints of that, right? You know, okay, let's go to 3D. Watch this one. You ready? This is going to be awesome. Let's start real basic here. Cos t, sine t, t. This is a 3D space curve. Again, I can try to plot points. This is going to be in 3D. It's going to be a little, you know, it's tough to plot those points and draw those vectors, but let's not plot a bunch of points. Let's use our human intelligence. If I ignored z for a second, what's going on in the xy plane? Beautiful, thank you. Circular motion. It looks like kind of circular, just like we just learned about circular motion with a radius of 4 and sort of an accelerated period, or a sped up a shorter period, which means I'm going faster than normal. A shorter period means I made it all the way around in a shorter time. I'm going a little faster. I have increased my angular velocity. That number 3 has something to do with angular velocity. Again, this is us putting physics on this math, I think. But it kind of helps make some connections.
Makes it go faster.
Right, that 3 makes it go faster. Thank you. Shortening the period increases the speed, right, that you went around, right. Anyway, back to this guy. If I ignored z, I have circular motion in the xy plane, radius 1. But the whole time it's sitting there going around and around in the xy, what's z doing? As time grows, as time goes on, what is z doing? It's growing up out of, so I've got circular motion in the xy plane, and then this z is growing. This is your classic helix, and I can draw it fairly easily.
Yeah, and the x and y have a certain range that they can go to with the z. It keeps.
The x and y have circular, what I would call circular motion of radius 1. Again, I could plug in a 0 and plot some points, but I think I would start here. And as I go around and do this circular motion in the xy plane, I don't... How about this? Watch this for just a second. If this z was a 0, what would that be? And you'd be stuck in the xy plane, wouldn't you? Your z would be stuck on 0, and you'd be a circle in the xy plane. But as time goes on, this z is rising, and so you are this, if you don't mind. Now look at me. I went around one time, and I'm right above myself. How long did it take me to go around, by the way?
2 pi.
It did take me 2 pi to go around. The period is 2 pi on this problem. If it took me 2 pi amount of t to go around one time, what would be my height right there? Good. If you plug in 2 pi, that brought you around one time, and your height would be, your z would be 2 pi. You know, so my picture is very misleading. Watch this. That's 2 pi. That's a height of 2 pi. That's a 0. This is a radius of 1. Something's wrong with that picture. Anyway, it's not to scale, because 2 pi is, what is 2 pi? 6. Thank you. Roughly 6. 6.28. Right. So anyway, that's supposed to be 6. That's a 1. I'm not to scale here. But I think it goes around this way. I should put little arrows on it. And that's just one trip around. The truth is, it goes again and again. And guess what? When t is negative, it goes back down this way. Oops, sorry. Oh my God. Oh, cut the video. That's horrible.
I took my eyes down for a second. Oh.
Sorry, something got off there. It's hard to draw a helix. It's a helix though. But what and drawing it might be fairly important. What's more important maybe is recognizing that equation and what it is. Recognizing the circular motion in one plane and then the rising z in the other and creating a helix. You could have a helix come out at you. How would you have the helix come out at you?
X is T.
Right, and you could make it more stretched out, I suppose, if you made it 3t and 4 cosine 2t and 4 sine 2t. Now there's a lot of crazy details going on in this, but I think I'd just like to say what you said. You said this is a helix, I think. I want to write this. I'm going to write a couple notes here. Circular motion in the YZ plane. So it's coming out at you in the X direction, I think. It's coming out at you in the X direction. It's got a radius of 4. It's got a period of 2 pi over 2. 2 pi over 2, which is pi. You're right. Okay, I'll try to draw that. Coming out at me. Radius 4. Circular motion in the YZ plane. I wonder where it starts. I think I'll just plug in a 0 and see where it starts. If I plug in a 0, 0, 4, 0, 0, 4, 0. Okay, that's right here. It starts here. Boy, I'm not sure. I'm going to guess it goes. I got the y being cosine. I got the z being. I'm going to guess it kind of goes this way, and it comes around, and it goes around that x-axis and comes back up, and there it is. Now it's out here. That's one loop around. It's hard to draw these little loops. It's taken me 30 years of practice.
So it's pi units in the X direction?
So, wait a minute. So what did I do? I just went around once. So you're saying that would be t equals pi? Because that's the period?
But then 3 pi units in X direction.
Oh, but how far is that for x then?
3 pi.
You're right. X is 3 pi. Again, it's kind of a bad picture. Well, not a bad picture, but a not to scale picture. The x-axis is not really to scale with the other axis, right? But that's just one trip around. It does it again, watch. And it ends up, there's another lap around. Here's another lap around. And it goes back into the board. I won't even try that.
The cup should have touched the 4 on the C, right?
It does not really touch that 4. It's out in front of that 4 because as it's doing, it's coming out at me a little bit. Right, right.
And directions.
And I should put little arrows that I'm pretty sure that's what I'm doing here. Yep. Yep. All right, you guys, listen. That's a pretty good introduction to 12.1. Now, I haven't told you everything, but I'm introducing you to vector value functions in 12.1. But I'm going to move on. And I tend to do this. Listen, by the end of the day, I mean, just, 20, 30 more minutes here, I'm going to get on into 12:3. Well, watch. You'll see. Don't freak out, though. Listen, if we have a vector valued function, we can take its derivative. I think I'm going to go back to this. I'm going to go back to something real simple. I'm going to go back to this t squared. You can take its derivative, you guys, r prime of t. And maybe you would guess, you're taking the derivative with respect to t, you call it r prime of t, and maybe you would, I mean, somebody should teach you how to do the derivative, because this is a new thing. This is a vector valued function. This is a new world you haven't been in yet. So somebody should tell you the rules. But you probably would assume the correct rules here. What would you assume? Very good. So your assumption is, if you're going to do a derivative, you would just do the derivative of the x component and do the derivative of the y component separately. And guess what? You're correct. That is how you do derivatives of vector valued functions. You do it with respect to t. It's a 1, 2t. By the way, let's do a second derivative. A second derivative, please. 0, 2. Yeah, good job. So listen, just telling you how to do a derivative is sort of 12.2. But in 12.2, they teach you, guess what? You can do derivatives. And they teach you the good old-fashioned long way of doing a derivative. They say if you're going to do a derivative, what you're doing is this. The limit, as the change in t goes to 0, r of t plus delta t minus r of t all over delta t. I don't know, they got a lot of this in 12.2, and that's what's behind us doing these derivatives, is this good old definition of a derivative. And if you follow through on this is sort of, they prove to you that you're allowed to just do the derivative of each component. You're allowed to do the derivative of the x component and y component and z component separately, like that. So I won't make you do any of that. I'm not doing that. But they kind of do this in 12.2, and then they make you do some derivatives. Okay, and then we get to 12.3. So it doesn't take me long to get to 12.3, and this is the beauty of this subject. You ready? This is the beauty of this. So I'm going to 12.3 now, and they finally, when I get to 12.3, they tell me this. If this original function is the position function, if it's position, and t is time, and this is position, and t is time, then what's his derivative?
Velocity.
Thank you. And what would be a second derivative?
Acceleration.
Acceleration. Right. Right. So we can talk like that. So maybe now you realize how I can go from 12.1 to 12.2 to 12.3 very quickly. I just did it. The book slows down. They stop in 12.2 and talk all about derivatives. And they don't mention velocity and acceleration, but I'm dying to get there. So I'm there. You're right. I can consider this velocity, and I can consider this acceleration. And what I love to get you to do is to sketch a curve and sketch some velocity and acceleration vectors on that curve. So let's do this. Let's...
We accelerated past the book.
That's right. Let's do this. I want to sketch this and illustrate all this at the point t equals 2. So I want a good looking picture here. Let's check this out. We already graphed this. It was this parabola. It was at this point 1, 1 when, this ain't the best looking parabola, but. It's heading this way. We think the motion was this way. Do you remember that? That's That's me showing orientation is what they call that, putting those little arrows on there. So at t equals 2, what was the position?
4.
Good, thank you. I'll just make these little notes. In other words, r of 2. It was 2, 4. That was the position. And remember, the position vector, listen to this. The position vector is drawn from the origin out to that point. And that's what kind of got me to this position. Again, I kind of like to erase that guy. I don't like to see him. He clutters up my picture. But the position vector took me to this point. Now I'm at that point. What would be the derivative evaluated at that point? At t equals 2, what's the derivative at t equals 2? 1, 4. Listen, when you draw this derivative vector, and you know what a derivative is. It's usually tangent to the curve. When you draw this derivative vector, you draw him on the curve. You don't draw him from the origin. So you go out to that place where you were at, right here, and you do this derivative vector, or I can call it a velocity vector, but I draw it at the point. I don't draw it from the origin. I draw it on the curve. And so guess what I do? I go over 1 and up 4. I go over 1 and up 4. And when I do, boy, it should look nice and tangent. That's my velocity vector. Blue, I'm making blue. I'm going to call him the velocity vector at 2. Cool. I called him r prime. I could call him the velocity vector. I can change the language here. I can call it v of 2. V now stands for velocity, I guess. All right, at that moment, I want to draw the acceleration vector. I want r double prime of 2. And it's kind of funny. It's 0, 2, right? There's no variable in there. It's just a 0, 2. And again, that's my acceleration vector. That's the acceleration vector at 2. And I want to draw it on the curve. And I'm going to use red for acceleration. And on that curve, at that position, the acceleration is 0, 2. Oops. It's supposed to go up, straight up. 0, 2.
So does the magnitude of the acceleration matter, and then kind of like the direction of the velocity is really what we're looking at?
There's a lot of things we're looking at. You're right. I mean, I've got at and all this stuff is at this moment in time. Keep that in mind. This is calculus, and we're doing all this at this instant. 1 instant later, at 2.1, I've moved, and the velocity vector probably grew, probably going a little faster. The acceleration is remaining constant, though, isn't it? In this particular example, the acceleration vector is always 0, 2. What if I went and, do I want to draw the acceleration vector right here? 0, 2. What about right here? 0, 2. What about right here? On this curve, the acceleration is always 0, 2. It's not changing. The velocity, I bet, is changing. The velocity is definitely changing direction. And not only does it change direction, it probably changes. A vector has direction and it has magnitude. And this velocity, as it changes, it's probably changing direction and magnitude. It's speeding up or slowing down, getting longer or getting shorter, I suppose. Let's check out this whole scene. I'll tell you what, let's check out this whole scene at t equals -1. At t equals -1, it won't take long. What's r of -1? That's the position. What is the position when you're at -1? Oh, that's at -1, 1 position. That was over here, -1, 1. What's the velocity at -1? 1, -2. 1, -2. Now, when I draw that, it should look like it's tangent to the curve. Let's see. Here I am. Again, my curve might be a little inaccurate, but I should go over 1 and down 2, over 1 and down 2. Well, I'll be damned. That looks pretty good, doesn't it? Looks sort of tangent to the curve. That's my velocity at -1. And my acceleration at -1? My acceleration at -1? Yeah, thank you. That's what it always is on this kind of boring graph. It's 0, 2, and we already sort of have it drawn there. There's the acceleration. See, I think this is why chapter 12 and vector value functions are so useful. You can knock out these derivatives, and these derivatives are easy to do, and their velocities and their accelerations. And then you draw them on the, I mean, it's just better than good old parametric equations. These vector value functions are advantageous for this purpose, I think, for this purpose. That's why they're so great. Not really for plotting the original thing, but for this derivative mode work. And these velocities and accelerations that you can draw on the curve. Hey, if I said the word speed, what would you say back to me?
Methamphetamine.
I knew that was coming. I should have caught myself. If I say the word speed,
Methamphetamine.
he says methamphetamines. Okay, back to here. If I say the word speed, what would speed be? What's speed?
The magnitude of
The magnitude of velocity. See, this velocity is a vector. And a vector has length and direction. Magnitude and direction. We studied that with vectors. A vector has magnitude and direction. But speed is when you're just concerned with just the magnitude of the velocity. So speed is the term we use when we mean this. The magnitude of the velocity vector. So watch this. Can you find the speed in general at any time? The speed in general at any time for this particular curve.
Just going to take the magnitude of the velocity.
That's right, and I'm going to do the magnitude of the velocity vector in general at any time, which would be the square root of 1 plus, yeah, good. That's the speed at any time. You guys told me earlier already, you said speed is a scalar. Well, notice how it came out. It's a scalar function, right? Look at it. It's not a vector function, right? I mean, it's just a f of, it's like a f of t, right? There's no vector there. Anyway, specifically now, what I got is this speed function that'll tell me the speed at any moment in time. I don't know. At t equals 0, what's the speed? At t equals 0,
1.
the speed is 1. At t equals 2, what's the speed?
3.
Really?
2 plus 4.
At t equals 2, the speed is square root of 17. Hang on a second. Is that what this one is? Hang on a second. Where was this guy? Oh, here he was. Yeah, look at him. What's the magnitude of this? Square root of 17. Yeah. I mean, I can find his specific speed, but I have a function over there for the speed at any time. I can use that, or I can use this, and I just discovered that this guy has a magnitude of the square root of 17. That's how long it is. I like to ask this question. Again, once you start using these words, velocity, acceleration, speed, we are sort of pretending we're in a physics problem. And the physics problem we're pretending we're in is a little particle is traveling on this path. I call this the path, and there's a little particle traveling on here, and that's his acceleration at any moment, and that's his velocity at any moment. I mean, we're drawing these things. It's awesome, What was I going to say? Oh, at this moment, do you think you're speeding up or slowing down, or can you tell what's going on? But it's kind of hard because it's at a moment. I mean, it's almost like if you're going to use the word speeding up or slowing down, you kind of need 2 moments, right, to compare. But I think we can get away with this. At this moment in time, what would you say?
Slow down.
Speeding up.
Slow them down.
All right, now we'll learn some better language. I mean, I don't want to go to 12.4 and 12.5 yet today, do I?
It's gonna have to do with the direction that the acceleration and velocity are opposite, the same.
Right, and so I can refine this language as this chapter progresses, but I got to save something for, we got 3 weeks. I can't tell it. But let's just answer the question. I would say speeding up, and I would say the reason is, just generally, it looks like the acceleration is kind of with the velocity. Kind of with it. Do you understand what I'm saying?
Yeah.
It's kind of going to help it out. There's some acceleration here that's going to help out this velocity, and in the next frame of the picture, the velocity should be bigger. And in the next frame, bigger. And in the next frame, bigger, I think. I mean, yes, I would call that speeding up at that point. I think it's just kind of obvious because acceleration is sort of helping out velocity in that moment. Acceleration is the thing that changes velocity, right? It does two things when it changes velocity. It changes the velocity's magnitude, and it might also change the velocity's direction. It might be pulling it a little toward here, a little bit. Huh. Anyway, over here?
Slowing down.
Yeah, and my reasoning would be, look, that acceleration is kind of dragging back on what velocity is. Velocity's heading this way, and acceleration's generally opposite. You hear me? I'm not clearly defining it, am I? I'm just saying, kind of, it's kind of opposing it. But that's good. You're right. Slowing down. Is there any moment when it's not speeding up and not slowing down? Is there ever a moment when it's doing that? You're right. At this origin, the acceleration vector still looks like that. The velocity vector would look like this, I believe, at this point, at t equals 0. And at this moment, your velocity and your acceleration are perpendicular. And that means that acceleration is neither contributing to or detracting from the next frame of velocity. It's not helping it or hurting it. There's nothing in that acceleration in the horizontal direction, so there's nothing contributing to the change in velocity at all at this moment. And at this moment, I would say what would you say? It's funny because it's at a moment. I mean, the next moment over, it's speeding up. And the moment right before that, it was slowing down. But at that moment, for just a moment, it was constant. Or I'm going to say, here's what I'm going to say. Neither speeding up or slowing down at that moment, at that one moment. Should I say nor? I meant nor. I don't know. Just at that one moment.
Wouldn't it be stopped at that moment?
Well, so you could say it. Ooh, that's a good question. Is it stopped at that moment? Now stopped would imply no velocity. It has velocity at that. It has velocity at that moment. So no, stopped wouldn't be appropriate, I guess. Although again, at any moment, if you really just take a snapshot of one moment, everything looks stopped. I mean, so I don't know. We can mess around with language and semantics and words but no, it moves on through there. The velocity is never 0. Oh, you could say the velocity is completely horizontal. There's no vertical velocity. You know, when we launch our projectiles, which is another physics topic, when it gets to the peak, we like to say, oh, it stopped for a second. But the truth is, it's still got horizontal velocity, but it's got no vertical velocity, right? Right. Yeah.
Here the horizontal velocity is always the same because the acceleration is only in the y direction.
Oh, okay, so now he's investigating something. he says no matter where you are on this curve, your horizontal velocity is always the same, because you can look at the picture and say the only thing acceleration is going to affect is your y value of velocity, or your vertical velocity. I guess you're onto something by looking at that picture. You could also just look over here. The horizontal component of velocity doesn't have a variable in it. It looks like it's going to remain constant. Right. The vertical part of velocity looks like it'll be changing. Yep. Yeah, you're right.